Okay, it'd be great perhaps if we can start with a little bit of background on the process of applying for and then obviously receiving the Royal Academy of Engineering Fellowship.
Hmm.
And I think it's around you're looking at energy consumption in data centers. So just a bit about
Yeah.
where the idea came from and the
Hmm.
process of getting the fellowship.
Yeah. So the Royal Academy of Engineering is awarded to very few people every year. This year, only 12 people have been awarded with this fellowship, and it's a 5-year project. In my particular case, I'm going to look into reducing the energy consumption of data center interconnects and regional networks. And my background is in multi-band optical transmission, where we extend the existing infrastructure that's already in place, for example, in C-band. And sometimes there are commercial systems for C+L band, which is an example of multi-band transmission. And this background, this approach requires different tools and equipment. One of them is amplifiers. And that's where I started working on bismuth-doped fiber amplifiers, which are a core part of the project here. In 2024, we've collaborated with National Institute of Communication and Technology in Japan and Nokia Bell Labs to do the world record data transmission in standard single mode, single core fiber. We've achieved 402 terabits per second, and it showed that the work that I'm doing can also help with achieving new horizons. But also it shows that that this approach is quite sophisticated. That's why I've started looking into what actually can I contribute to and which problems I can solve. And I realized that there is a huge demand on the traffic growth of the data center interconnects and regional networks, and at the same time, a big pressure of energy reduction, and that's where the idea come from.
Okay, yeah. I mean, I think you've explained a lot of it there already, but in terms of what you're doing, you're looking at fiber optic networks,
Hmm.
power consumption, um, I think specifically related to data. I mean, everyone's probably aware that AI is exploding and data centers are struggling to keep up with the demands, both in building them and the power demands. So, just your thoughts. I mean, how do you have any thoughts as to how problematic power and data centers as a sort of equation is at the moment?
So if we talk about the power consumption in general in data centers, we understand that the most of it is coming from cooling and computing. But there is a more and more approaches that rely, for example, on distributed computing, where we then need high-speed connectivity between either quite distributed parts of the data centers or even data centers located in different parts of the world. And that's where this approach that I'm developing can really help, because it looks into extending the traffic of these links and at the same time reducing the energy consumption.
Okay, and you mentioned the bismuth doped fiber amplifiers, but specifically what you're doing, I think, is looking to bring together those. So bismuth doped fiber amplifiers
Hmm.
and optical frequency combs. So please tell us a little bit more about
Hmm.
how you've arrived at that sort of
Yeah.
solution and what do you think
Hmm.
it brings to the party when it comes to potential power savings when it comes to networks.
Hmm. So bismuth-doped fiber amplifiers is quite unique because bismuth is post-transitional metal, and we can tweak the fiber structure in a way to achieve gain in different wavelengths range. And in this particular project, we will be looking into O-band transmission, optical O-band transmission. And O-band is very attractive in a way that there is a zero dispersion. It gives some troubles with operating, but at the same time, it can help reducing digital signal processing quite significantly, especially if we're talking about coherent transmission. On the other hand, and bismuth obviously works here very well, and core part of the project is to develop an energy efficient bismuth-doped fiber amplifier, particularly for the O-band coherent transmission. On the other hand, the optical frequency combs, it's just like perfectly synchronized DFB lasers. So we know the phase differences between each of the lines, and it also can help us significantly reduce the complexity of the system. They can be quite small, so they are very often the on-chip devices. And then because we know the phase difference between each of the lines, we can also reduce significantly the digital signal processing of our signal. And in total, using both of these approaches can reduce the energy per bit consumption by 30 to 40%.
Okay, so that's it. I think if I'm right in understanding it, your primary driver is obviously that energy reduction, which is quite significant. But alongside that, there's the benefit, and I think you might have alluded to it at the start of the conversation, greatly increased transmission capacity. So what's the possibilities there, if you like, which is quite exciting.
Yeah. So if we take a classical transmission link, we would mostly think about C-band. I mean, the regional network, for example. And the C-band is not quite big. It's around 5 terahertz of bandwidth. We can potentially transmit around 80 DWDM channels there, and the capacity can go up to 32 terabits per second. So the number around that. We can push it a bit further if we are happy to sacrifice the reach, but overall, that's how it is. If we take the O-band, the whole O-band spans over 17 terahertz of bandwidth, which is 3 times more than the C-band. And this bismuth-doped fiber amplifier that I'm building can help to cover this whole band. So just through the increased bandwidth, we can achieve much higher throughput, but also because there are options to increase the modulation formats, and the reach that we're looking into achieving is not very long. We can push that up to 200 terabits per second in just one fiber.
Okay, right. Okay. And in terms of the project, you're obviously the brains behind it, shall we say, but you've got a range of organizations from, I guess, it's top to bottom of the telecom supply chain. So give us some idea of who again, I think you mentioned a couple of names, but who are you working with, and what are those partners, if you like, bringing to the project?
So there is total 8 partners in the project, and the brief overlook of this project include the device suppliers like Lightera and Pilot Photonics. Then there is equipment manufacturers like Coherent and Nokia Bell Labs. And finally, on the top, there is one of the I think the biggest telecom supplier in Japan, KDDI, which will help us to look into the real deployment of the systems and use their dark fiber facilities in order to proof test the technologies in the real field environment.
Okay, and in terms, I mean, you mentioned again earlier, I think that obviously a large amount of the power required in the data center is around the cooling, for example. But I suppose it'd be good to understand how important you think that your sort of network related energy efficiency innovation here will be for the data centers. It sounds as if it's not insignificant, but just compared to the sort of the compute power required, cooling, etc. Just where do you place it?
Right now, it takes about 5 to 10% of the overall power consumption, but this number can grow in theory because of how we use AI at this moment and how we want to move AI to be more efficient. If we try to distribute the computing powers a bit more, we will require more links to connect different data centers, different parts of the data centers together. Right now, this solution is usually made in a more brute force way, when we would have a very large cable with a lot of C-band parallel fibers going on. But this approach that I'm developing can help with the tackling with the further scaling this up, or either reducing the number of fiber pairs to transmit the data that we need. Overall, this approach can also help us to extend the reach in particular cases. And if we have a possibility to transmit the same amount of data, but to a longer distance, this can help us to achieve a better distribution, which can, in fact, reduce the requirements for the cooling as well.
Yeah, no, I get that. And in terms of, you said the project's a 5-year project. So,
Yeah.
Do you have any particular sort of, obviously you work on, but what's the plan? You mentioned KDDI. Do they sort of have exclusive access to what you then develop, or how do you anticipate your innovation being brought to market over time, I suppose?
Right. So there are different possibilities, obviously. So one possibility is some part of the work might be possibly patented. Another route is the obvious commercialization of the parts of the work where IP is generated towards, for example, bismuth-doped fiber amplifiers. We're looking into those solutions as well. But in general, my overall approach is, yes, I have 8 partners. They all are quite unique players on the overall optical communication, either research or market. But I'm always open to new collaborations, looking into new possibilities of extending the impact of this technology to maybe something that is not originally in the proposal, but because Royal Academy of Engineering allows us to divert a bit, as long as we stay on course of actually delivering the impact, then there is no problem of collaborating with other people and investigating some other approaches that can, in fact, make this project more beneficial.
Okay, and in terms of the sort of timeline and challenges, I mean, you know where you want to get. Do you anticipate a relatively smooth, it's just a question of time, or are there any particular challenges that you think might take a large amount of effort, or you're not 100% sure that you can overcome, or you're pretty sure that you can get everything in place, but it's just the time taken to prove it all, if you like?
There are obviously some risks that something will go wrong. Because the project is at quite early stage, it's hard to say which of the components and parts might go wrong, but so far everything looks quite promising. In some aspects, I am running slightly ahead of schedule. So there is a progress already on, for example, amplifier design and modeling, and development of O-band coherent transmission test bed. So this is all work that has been planned slightly ahead. So for the year 2, 3, but it's already starting to being delivered at this particular time. Another aspect is, for example, a good example of diversion and how this project might be slightly different from how it has been written is with recently again collaborated with National Institute Communication Technologies in Japan and achieved yet another world record transmission of 430 terabits per second per one standard single core fiber. So there is I'm quite positive so far about how this project develops, and I'm looking forward to see where it's going on.
No, that's fantastic. I mean, it sounds very exciting, and maybe we can touch base in a little while to see how you're going. But at least for now, Aleksandr, it's been great to chat, and thanks so much for sharing insights. Appreciate your time. Thank you.
Thank you so much for inviting me again. Thank you.